Hello everyone and welcome back. Now in the previous video I introduced you to auxiliary function methods for dynamical systems. We really just scratched the surface, but what you saw every time is that two things are involved. The Lie derivative and inequalities on the state space as a variable, functions of the state space. Now what I would like to do in this video is introduce you to a method of verifying these inequalities, and in particular tuning coefficients of polynomials to make functions greater than or equal to 0, for example. Now here's what I want to do. I want to start with a general setting here of trying to ask myself this question. Is my function greater than or equal to 0, say for all x in Rd, for example? Now this is a hard question, right? This is, maybe you can use a little bit of calculus, try and find the minimum of this, but it could be a very, very complicated problem. And so, it's not the easiest thing in the world. What if I tried to make it easier? So what if I said that this is polynomial? Does that make it any easier? It certainly feels like it got easier, right? Polynomials feel like they're easier to work with. We spend like a lot of high school and early university learning polynomial functions, dealing with polynomial functions. Real analysis, you learn all kinds of approximation theorems with polynomials. It's got to be easier, right? It's got to be easier than general functions. Unfortunately not. It's still a very hard problem. In fact, verifying that a polynomial is non-negative over some set, it turns out often to be an NP hard problem. So very, very difficult problem that we're going to try and avoid doing here. What if I told you that this function could be represented as a sum of squares? Now, I'm going to call this an SOS. And essentially, the hope here would be that I could represent the function f as a sum of square functions. Let's say gi over some finite number of functions that are all squared. Then I can very easily answer this question, right? Squares are non-negative, sums of them are non-negative, and therefore this is true trivially, right? So the question here becomes, instead of maybe asking myself, is this thing non-negative, for what's written on the board, this becomes equivalent to saying, could I find a sum of squares representation, right? So let's actually go by example here, okay? Let's try and do this with a very general polynomial. Here's my polynomial, okay? I'm gonna work through this by example. Polynomial in two variables. Let me write it down for you. 13x1 to the 4 minus 6x1 cubed x2, right? So I've got to get the iPad up here so that I can't make any mistakes for you. x1 cubed plus x1 squared, x2 squared, plus 10 x1 squared plus this thing is horrible, right? 12x1 x2 squared plus 4x2 to the 4. I think I've got that right. Okay, so you look at that thing, and here's my question, right? Is that a non-negative function? Okay. Well, okay, that is non-negative. That's okay, check. This one, no, because I have odd powers and I've got minus signs. I got odd powers. Okay, this one is, that's good. This one is, okay, but odd powers. This one is, okay, so it's not written as a sum of squares, right? But of course, that's not the only way to write a polynomial. This is just written as a monomial expansion, right? But maybe when you took a high school calculus class or a high school functions class, you learned about completing the square, right? So even functions that didn't look like they were perfect squares, often if you recast them in the right way, they turned out to be squares. What if I told you that this function is equal to this representation? Let me get the iPad out again here just so that we've got it all down. x1 squared all squared plus, and you can feel what's happening probably, right? 2x2 squared squared plus x1 x2 minus 3x1 squared squared. But now take a look at what I've just written down here in a different color. Okay? Function squared plus function squared plus function squared. This is greater than or equal to 0. This is a sum of squares representation of a different function. It is exactly what I just said right here. And of course, the sum of squares representation automatically, trivially verifies that this thing is non-zero. So the question is, Jason, how did you find this? How could I find this? How could I verify that functions are non-negative myself? Well, it turns out that if you want to find a function p to have a sum of squares representation, so here I'm just talking about p as just a general function now, a general polynomial. If it can be written as a sum of squares, it has to be written as a vector of monomial terms. I'll show you what this, I'm going to show you by example, but I'm going to say z of x. This is a vector of monomials, so maybe x1, x2, x1 squared, x1 times x2, x2 squared, for example, times a matrix P times the same vector. This is a bilinear form. You probably saw these in linear algebra, or if you, especially with the Rayleigh quotient. And in particular, this thing is greater than 0 when, or if and only if, this thing is positive semidefinite. In particular, you can make this thing greater than 0 when p is positive, or it is positive definite. So essentially, that tells us that we can verify non-negativity of this thing if we can find this bilinear form representation. And in fact, what I'm going to conjecture to you is that this is a sum of squares representation. Because if p is positive semidefinite, it has a matrix square root. That means that there exists a matrix Q, so that Q transpose times Q is equal to the matrix P. This is a matrix version of square root. These don't have to be square matrices. P does. And so what you can see here is that this really just becomes this right here, Q times Z of X in the L2 norm, which is itself a sum of squares, right? So it's just, if you want to sort of write this thing out, you're going to have each component qz of x I in this vector, and then all squared. So this is actually a sum of squares representation, and it tells us that sums of squares come from positive semi-definite matrices. So the question was, Jason, how did you know that this thing was a sum of squares, right? Well, of course, I gave it as my example, so I better know. But in fact, if I go back to this example here, I get p of x1, x2 is equal to, now my vector of monomials here, if you take a look at this thing, the degree inside the vector of monomials is going to be half of the highest degree that you're going to see in your function here. And that's because if this is degree 2, this is degree 2, those things will come together and give you degree 4. So in fact, you can write this function in this way using the following. Here, let me write it out for you. Again, let's get the iPad out just so that I'm right here. x1, x2, x1 squared. So this is my vector of monomials all the way up to degree 2. Transpose, and then my matrix P becomes 10, 0, minus 2, 0, 6, 0, 0, 0, 0, 0, so a row of zeros, minus 2, 0, 13, minus 3, 0, 0, 0, minus 3, 1, 0, so Not very fun right now, just sort of copying numbers down, but I really want you to see this. So it's important that you sort of understand what's happening here. And then my last vector of monomials, x1 squared, x1, x2, x2 squared. And in fact, you can check if this thing is equal to p, then my q is equal to 1, 3, 0, 0, 0, 0, minus 2, 0, minus 3, 0, 0, 1, 0, 2, 0. And those numbers should look very familiar to you. 1 and minus 2, right? So x1, x2, x1 squared. 1x1 minus 2x2, all squared, just like the representation tells us. Then 3x1 and 2x2 squared, right? And then minus 3x1 squared, x1, x2. Just, I just wrote the minus second here. But now you can see this. But of course, this is a cumbersome process. This is not something you want to do every day, just sitting pencil and paper, try to find these things. In fact, we have software that will do this for you, okay? So in fact, if you feed in a polynomial, the software which I use, which is called YALMIP, will translate the problem from this side that you gave it into this side right here. It will translate it into a problem of finding the semidefinite matrix. And then, because you now have a problem of finding a semidefinite matrix, this becomes a semidefinite program which can be solved using an interior point method. In my case, I use Mosaic, although CVX works, and there are many, many other problems that do this. And essentially what they will do is they can help you to find these representations of sum of squares polynomials. But it can do more, okay? Let me go back to Lyapunov functions for a second, okay? Let's do this. Lyapunov functions. So remember, the first two conditions for Lyapunov functions was that v of x is greater than or equal to 0. And the second one is that v of x dotted with the dynamics of the right-hand side is less than or equal to 0. Okay? And then the third condition is that it opens up, but let's just deal with these two. These are inequalities. Here's what I could do, though. I could take v to be a sum of monomials. So let's say a sum of, let's call this Cij of x1 to the I, x2 to the j, up to some power. So let's say 0 less than or equal to I plus j, up to the power alpha, for example, right? Well, then take a look at what this becomes, okay? So maybe I want to, I have a problem of finding coefficients and verifying non-negativity all in one step. But what I could do is I could tune the coefficients to create these things to be sum of squares instead, right? So this is something that can also be handled by YALMIP and Mosaic. In fact, Mosaic can solve these problems. So YALMIP will translate it into the sum of squares program. YALMIP will solve these things using an interior point method in such a way that it simultaneously verifies sum of squares representations, giving the inequalities you want. This case would be a negative sum of squares, of course. And it tunes the coefficients to give you the Lyapunov function, right? So this is a way of using sum of squares programming in order to find Lyapunov functions. In fact, you can do this for time averages too, which we'll see in the next video. Now, the question that you might have for yourself is, Jason, is it true that every non-negative function has a sum of squares representation? Unfortunately, the answer to this is no. This was actually proven by Hilbert that in general, if you have a general, d-dimensional space and you have a non-negative polynomial on that space, it is not necessarily the case that you have a sum of squares representation. And it wasn't for like 40 or 50 years that Motzkin came along and actually found a polynomial that is non-negative, but does not admit a sum of squares representation. He used the AM-GM inequality in order to prove that. So you can look it up. It's called the Motzkin polynomial. It's very, very famous. But so this is not an equivalent condition. Asking for sum of squares verifications of inequalities is a strengthening of these conditions, but it is a computational strengthening. Remember, we started with this being an NP-hard problem. This is something that can be solved using well-established computational software in reasonable time. In fact, let's take an example of finding Lyapunov functions using sum of squares programming, and in particular semi-definite programming. We're going to use the Moore-Greitzer equation. So you have it right here at the top of the board. In fact, this has an equilibrium point at 0, or at the origin. It is unique. In fact, it looks like it's globally stable in the sense that if you simulate the system, it looks like everything falls into 0. And so one would conjecture that maybe there's a Lyapunov function that can prove this kind of global stability. So if you just take a look here, the way that we're going to implement this using sum of squares is that we're going to look for a Lyapunov function v, so that v minus x1 squared minus x2 squared, it can be written as a sum of squares polynomial. Now the question is, why did I do this term right here? This promotes a strict inequality in my system. So for example, remember the condition is that I needed v greater than or equal to 0 for condition 1, but I also said that there's a condition sort of 1 star that strengthens this, that says v is greater than 0 when x is not equal to 0, right? Now, unfortunately, you can't deal with strict inequalities on the computer, but you can sort of fudge this a little bit. And the way that we do this is we say that v minus a function we know is strictly non-negative is greater than or equal to 0, which tells us that v is greater than or equal to x1 squared plus x2 squared, which is greater than 0 when x1 and x2 are not equal to 0. So that's all that this is doing. It's promoting strict inequalities. It's kind of a cheat code. And then I'm doing the same thing with the Lie derivative. Again, sum of squares are positive, so because I need the Lie derivative negative, I have a negative Lie derivative here, and I have that same forcing of strict inequalities. Now, as I said, I'm going to use Yalmip and Mosick. These are free downloads if you're an academic. They are very easy to get. I will put the download links in the description to this video, so you can run this on your own. I highly recommend having a little fun with this. And so let's take a look. Let's clear up everything. Here's what I'm going to do. I'm going to start by looking for a Lyapunov function that is a degree 2 polynomial. So I want to remind you that in this search, there is a hyperparameter that is the degree of the polynomial you're searching for, right? So I'm going to start by saying maybe there's a degree 2 Lyapunov function, right? If there isn't, it doesn't tell me that there's no Lyapunov function. It just says it couldn't find a Lyapunov function that was a sum of squares, right? So you have to be careful about what the verifications mean here. Here, I'm using the symbolic variables. This is x1 and x2. That's with the 2×1 vector here. These are symbolic variables. They're semi-definite programming variables. This is coming from Yalmip. Here's the right-hand side of the Moore-Greitzer equation. Again, we're going to need that for the Lie derivative term, the f dot gradient of v. Here I'm going to make a polynomial for my Lyapunov function. So I'm going to call this v. It's going to be a polynomial in the variables x going up to degree v, starting at degree 1. There's not going to be any constant term in here because it doesn't matter for Lyapunov functions. And then I'm going to compute some derivatives. And here's my Lie derivative here. It's the dot product between the derivative or the gradient of the Lyapunov function and the right-hand side. And now I'm going to define my sum of squares program. Here's my constraints. I need to write v minus x1 squared minus x2 squared as a sum of squares. So that's what the SOS of this means. Similarly, I want the negative of my Lie derivative minus the x1 squared minus x2 squared to be a sum of squares. That's what this means. And I'm going to, because this is an optimization problem and because infinitely many v's can satisfy this thing, I'm going to promote sort of interpretability. I want small coefficients in my Lyapunov function. You can promote whatever you want. It's just that in my case, I'm going to give this an objective of minimizing the L1 norm of the coefficients of my Lyapunov function. So let's take a look at this. Let's see here. So YALMIP is starting up. It's cleaning it up. And unfortunately, it couldn't find a solution, right? So it says there's an unboundedness in the problem, and there is no Lyapunov function that could be found. So the question is, does that mean that there's no Lyapunov function for this system? No, it just means that the computer couldn't find a sum of squares representation for a degree 2 polynomial that would be a Lyapunov function. So let's try and increase the degree here. Now we need this to be an even degree because we need this inequality to hold everywhere. So if it was an odd degree, that wouldn't hold immediately. So we'll jump up to degree 4. We'll restart this thing. Let's take a look. Here it goes. And, oh, sorry, we need to jump to the next section because it'll tell us if we got a Lyapunov function or not. Here we go. Lyapunov function has been identified. Here is what we have. So I'm just printing this out. I mean, it's ugly because it's a MATLAB printout, but the Lyapunov function is, all these numerical coefficients, x1 squared minus, this quadratic term, and then, here's more quadratics, here's the cubic terms, right? So it's a big, old, ugly thing here, but it's a Lyapunov function, at least a numerical Lyapunov function, right? So everything is true up to numerical inaccuracy here. In this case, the numerical inaccuracy comes from these interior point methods trying to solve these things and get these sum of squares representations. But for the most part, I mean, this is a verified numerical Lyapunov function. And you can restart this. You can go to higher polynomial degrees if you want. You'll still find the Lyapunov function. We know that Lyapunov functions are not unique for dynamical systems, so you might find another one with different coefficients. Again, here, this one has completely different coefficients, but that's also because it goes way, way up to degree 6. And we can try and plot it. You can see that nice bowl shape that we would expect from a Lyapunov function. The last thing I want to point out, condition 3 is automatically satisfied by this, by imposing this. That's why I only worked with 2 conditions on my Lyapunov function today. So as you can see, from this video is that we can use sum of squares programming and semidefinite programming in particular to identify auxiliary functions, and we can be clever about the implementation to make sure that maybe strict inequalities are verified, or we can bunch up some of these inequalities in order to reduce the numbers that we needed, right? We needed 3 conditions for the Lyapunov function. We got it down to 2 by this little strict inequality condition. So really, the magic happens between asking the question and putting it into the computer. You have to sort of string together the conditions in such a way that your computer can actually solve it for you and give you the answer you want. Now, I'm not going to go into this, but in the book, in section 4.2, there's a much more complicated example that identifies trapping boundaries to prove the existence of heteroclinic orbits. That requires a lot of sort of ingenuity. So if you want to see, an example of this with a ton of moving parts that's coming from a paper that I wrote, go check out the textbook, section 4.2, where I introduce the sum of squares representations, and you'll get a lot more out of it. Now, when we come back in the next video, we're going to start doing this at the data level. We're going to try and find Lyapunov functions in data. We're going to try and bound time averages from data, okay? So that will be a coupling of these methods with the Koopman operator and extended dynamic mode decomposition that we learned earlier. And in particular, the correspondence comes from these auxiliary functions and the Lie derivative being associated with the Koopman operator. So I'll see you all in the next video, everybody. Thanks for joining.